Okay, good afternoon, everyone. I am very pleased to have the opportunity to talk to you a little bit about how RRTC's carbon capturing composites can not only reduce CO2 emissions, but we can even put those emissions to work for us by adding value to our materials. We've got a lot of ground to cover, so I'm going to just jump right into it. So, with the world's population rising and more of the developing world industrializing, we are emitting increasingly amounts of CO2 over time. If we keep going down this route, we are going to end up in a bad place. We're going to have a lot of problems associated with climate change. In fact, there was a report out this month out of the Max Planck Institute which indicated that the average family of 4 emits enough CO2 over 30 years to basically eradicate about a football field's worth of Arctic ice, which is obviously going to contribute to the rising sea levels. In addition to that, we could end up disrupting the marine ecosystems with acidified oceans. Obviously, none of this is stuff that we want to happen. But we at RRTC think that we have a way to do our part in slowing climate change and creating healthier oceans by reducing these CO2 emissions. So before I go into that, I'm going to take a step back and take a look at one of the major contributors to CO2 emissions, and this is the transportation sector. Vehicles are responsible for close to 1/3 of all worldwide annual CO2 emissions, and that amounts to over 10 billion tons of CO2. That's a lot. That's a big piece of the carbon pie. So breaking that down further, about 1/3 of that comes from just the shipping and logistics sector, where, of course, the rest of it comes from other vehicles like automobiles and aircraft. We think that we can make a significant dent in that contribution with our solution. Of course, there are other emission sources that come from other activities like power generation and manufacturing, and we think we can actually make a difference there too. Speaking of manufacturing, here's a bit of perhaps less conventional wisdom. Very little of what we manufacture is actually carbon neutral. In fact, little to none of it. If you really want to have a truly carbon neutral process for making a material, you better have raw materials that come straight out of the ground, and you better have a completely renewable energy source to do the process with. Of course, a lot of the solutions that we're seeing at the ocean exchange here might be able to help with that. But anyway, so as much as I love the idea of zero emissions vehicles like the Tesla, those two are guilty of having a positive carbon footprint. And this is because a lot of the advanced materials that go into vehicles like the Tesla, their manufacturing processes consume a lot of energy and they emit a lot of CO2. And in addition to that, if you charge the battery in your Tesla with a power that comes from a coal-fired powering plant, you're going to end up with a CO2 footprint coming from that too. So going back to the materials aspect of things, carbon fiber is kind of the premium, high-performance material of choice for vehicle structural components. Unfortunately, not only does this material have a big footprint problem with energy and carbon, it also costs a lot to make, on the order of tens of thousands of dollars per ton. This is very far from ideal. So, this brings us to our idea. What if instead we make vehicle structural components out of a material that's lightweight and it captures CO2 during its manufacturing process, and that manufacturing process is cheap and has a low energy footprint? This sort of paradigm would have sort of a twofold result, where one, we end up offsetting some of the vehicle's emissions by capturing CO2 within the materials that make that vehicle, and two, the lightweight the lightweight of the vehicle ends up leading to fuel savings, which of course is going to lead to less CO2 emitted. For example, if we could have a material that we could put into vehicles and reduce their weight by 20 to 25%, we could end up saving up to 3 billion tons of CO2 emissions per year. That's a lot. That's about 10% of all CO2 emissions. So you're probably thinking, okay, that sounds nice. How the heck do we do that? Well, that's where our unique hybrid carbon capturing composite comes in. Unlike other composites, which are already available on the market, which are generally made of a plastic that binds together a reinforcing material, which could be a carbon fiber or an inorganic filler, our material contains a reinforcing component that actually captures CO2, reacts with it, and incorporates it into a crystal structure up to 40% of its own weight in CO2. And this creates a very, what we would call a geologically stable material, which will last for, a billion years. Like Crosby, Stills, and Nash say, we're all billion-old carbon. Anyway, in addition to all of that, our material is able to be engineered to have high performance properties. For example, we can make a material that's half the weight of aluminum, 5 times less heavy than steel, and still has decent rigidity and strength and environmental resistance properties. So, again, our composite material is made of a mixture of the plastic and this carbon capturing reinforcement material. The plastic can come from a variety of different sources, from recycled plastic bottles to more environmental type of materials like algae-derived agar. However, the real secret sauce in our composite is this carbon-capturing mineral. This carbon-capturing mineral is known as calcium silicate. It is very abundant in nature. It's found in a lot of different places. And, therefore, it's very cheap, on the order of less than $100 per ton. You can see how this compares to, carbon fiber, which costs, more than $10,000 per ton. So, we make this material by mixing the plastic with this mineral. We take the mixture and form it into the shape or part that we want, and then we take the part and put it through a curing process where we expose it to a mildly heated environment that contains both steam and CO2. Once that curing process is done, we have our hybrid composite part ready to go for whatever application it's needed for. So, since this is the ocean exchange, some of you could probably appreciate where we got some of our inspiration for this material. Seashells. Seashells are made of a tough hybrid composite biomaterial known as nacre. So we thought, well, why not, try to mimic this material? It's a nice material, right? So what we did was we 3D printed a plastic scaffold, and then we infiltrated it with our carbonate, mineral material. And we ended up with something, pretty tough, and it had good compression strength. So we decided, let's try to build on this success and, make this a material that we can make with a much simpler process. So that's where we're going with that. Speaking of building on past success, I just wanted to mention that RRTC is actually a spin-off of a company called Solidityologies, which is proving the ability for us to be able to use a carbonate cement to pretty much revolutionize the cement and concrete industry. That's a pretty big market. Billions of tons. Very high volume, billions of tons of material. So Solidia has actually gotten the attention of one of the biggest players in the cement and concrete market, and such that they have actually licensed the Solidia technology for these types of applications. RRTC wants to sort of repeat this type of success and the, I guess, so-called advanced material space. So that's why we're looking at these composite materials. So with all of the promising attributes of this composite material, we've made a preliminary identification of some target markets for this material. We are looking at making creep-resistant seals and gaskets. In fact, RRTC has an ongoing dialogue with Garlock Sealing Technologies, which is one of the leading entities in the seals market. If we're looking further down the road, we think that our stronger and stiffer composites can go into vehicle structural components like truck panels, as the guy mentioned in the video, And later on, maybe we could get into boat construction and maybe even container construction, like shipping container construction. But before we get to that, again, we're kind of in a preliminary stage here. The technology is still kind of early in its development. We need to do some things before we can really get people who are in our target markets interested in licensing our technology. One of those things is to demonstrate that our process is scalable, which, based on Solidity's results, we have a really high confidence that we can do that. The other is to demonstrate that we can produce our material fast. Sure, we have a really huge raw materials cost advantage with our composite. But if we can't make our material fast, then that advantage is going to be completely wiped out. The other part of things is, how do we deliver the CO2 for incorporation into the material and do it in a way that doesn't cost a lot of money and doesn't itself have a huge CO2 footprint? I think that's our biggest challenge, but it's also where we could make the largest impact on society in a positive way. So here's our really big idea. First, we should ask the question, how do we distribute CO2? Well, as things stand right now, the CO2 distribution market is really dominated by four really big companies, and they do pretty much everything. They distribute CO2 in compressed gas form, refrigerated liquid form, and dry ice. Unfortunately, these methods are very energy intensive, somewhat expensive, and they themselves have about a 20% CO2 footprint penalty. So, and in addition to that, they only have to address a CO2 market of about 500,000 tons. If we were to have a widespread adoption of carbonate materials technology, that market would shoot up to on the order of tens of millions of tons. So the current distribution network would not be able to handle that, and even if it could, it would not be sustainable. Luckily, some folks in the Rutgers labs have invented a process technology that actually allows for low energy decarbonation of materials. So if we were able to combine this decarbonation process with our carbonation process, both low energy processes, we would end up having a low energy, low cost recycling paradigm, sort of, I guess, what you would call a carbon capture, storage, and supply model. So, this type of thing we can do with very simple equipment, very simple materials, basically bricks. So pretty much anyone from any walk of life could participate in this type of economy. So just to show you an example of such an economy, we would send bricks to a coal power plant, for example. The bricks would capture the CO2, and then the bricks would be delivered to the consumer of the CO2, whether that be somebody who's making our carbonate materials, or somebody who runs a greenhouse, or even somebody who's just trying to serve some good beer. So, again, the technology is very simple. Pretty much everyone can participate. So we have a pretty big vision for the future that would be enabled by further development of our green technologies. And we would be able to, of course, meet some of the UN sustainability goals, some of which I have listed on there, one of which I don't, which is number 12, and I think that's actually the most important one, which is a sort of sustainable production and consumption cycle. So every big vision like this needs to have a visionary behind it. And at the center of this one is Rick Ryman, who is with me today. He is a distinguished professor at Rutgers University, and he's the founder of both Solidia and RRTC. He is a very successful serial entrepreneur. As for me, I am the senior founding engineer of RRTC, and I was the one who worked in Rick's lab and sort of developed this hybrid composite technology, and I'm looking forward to working with our winning team to take this material to the market. As for financials, we just actually received several months ago our Series A venture capital funding, which will be used for market discovery, validation, and IP protection. If we meet certain milestones, we'll be entitled to a second tranche of funding, which will be used for pilot plant and de-risking. We also have some grants with the DOE that we're targeting to help with the carbon capture and sequestration technology. And if we are fortunate enough to win the Ocean Exchange Prize, we will put a majority of the funds towards hiring a new engineer because we really need to expand our team. And we would use the remainder of the funds for capital equipment and consumables that would be used in the research. So I hope you have enjoyed hearing about our technology and how we might reduce CO2 emissions. And that's all I have to say. Thank you, and I'll be glad to take your questions.
Thank you, Kevin. Great stuff. So, any questions? You know, some presentations are just that good. They're just that, okay.
Thanks for the presentation. So you've got this new material, and you are going to displace existing materials. If so, what are they? And secondly, if you're looking at a environmental CO2 play, have you done a life cycle assessment around your entire process, and what sort of carbon reduction do you get for cradle to grave?
Okay. For the first part of that question, at the second part of that question, I'm actually going to ask Rick to come up and help me with answering that. But the first part of your question, as for what materials that we might replace, one of those might be, like I mentioned, these truck panels that are made out of fiber reinforced composites. That's one type of material we could replace. I will say that we're not quite, I mentioned carbon fiber. I will mention that we are not quite at the point yet where we are able to completely replace carbon fiber composites, but we're pretty confident that we're on our way to being able to do that. And as for the life cycle thing, what do you have to say about that, Rick?
Okay, so there's different ways of looking at it, but doing life cycle analysis where we're literally taking raw materials straight out of the ground. For example, in the Catskills, you can mine calcium silicate straight out of the ground. When you look at the entire cycle, that is the energy to take it out of the ground, the transportation to bring the mineral to the manufacturing facility, every step you could imagine. The material has a carbon negative footprint of minus 11%, which is a very good number. I haven't seen anything in the literature where everyone has laid out every single number where you can actually take in more CO2 than you actually emit. If we actually make the calcium silicate industrially, which can be done as a drop-in technology at a conventional cement mill, then you'll end up having a material, at least this, the binding material itself is about 30% carbon positive. But that's really an incredible number, because if you just think about it in the world of concrete, where you have 4 billion tons of concrete being used, 4 billion tons of CO2, and all of a sudden you're dropping that emission by 70% just by dropping this technology in place of Portland cement. That is a spectacular number. Now, if you compare what Kevin's talking about, which is a fiber-based composite, the fibers you put in there will still be somewhat damaging to the carbon footprint or life cycle analysis. But one of the things that wasn't mentioned that's very important is that when we do the carbonation process, we can take a plastic and we can increase the stiffness by a factor of 10. And in the past, that's only been done with fibers. We don't have any fibers in there, folks. So that's a really big benefit. The other thing is that when we're working with plastics, we can drop that plastics concentration right now to something on the order of 20%. So we're replacing it with something that actually consumes CO2. It costs way less. We're talking $3 a kilogram versus 5 cents a kilogram for the calcium silicate. So it's huge in value creation, and it's huge in reducing CO2 emissions.
All right. Next question, right over here.
Hi. great presentation. Can you talk about the increased environmental costs due to the mining of the calcium silicate?
So, yes, there is a little bit of a positive CO2 footprint associated with mining.
I'm not talking about the carbon footprint, but the other environmental degradation due to calcium silicate.
Oh, you're talking about like, having to make quarries and all of that sort of thing.
The water quality impacts and the sinkholes and things like that. So have you thought about that, like increased environmental degradation due to the mining versus the decrease in the carbon footprint? How does that weigh out?
Well, one actually really good thing is, and again, there's a lot of ground to cover, so there are a couple things that I missed mentioning during the presentation, is that, yes, we can mine the calcium silicate, but we can actually also make it synthetically.
Right.
So, the short-term solution obviously is to mine the stuff, but once we really refine the process to making it synthetically, and it's actually done with a process very similar to the decarbonation process I described, very, very low energy, then we don't have to worry about mining stuff anymore and, all of the problems associated with that.
Great. Thank you.
Oh, yeah, he's got a point.
My nickname when I'm not teaching is I've been called the MacGyver of ceramics. We've literally gone outside our office, dug up the dirt there, and as long as we combine it with limestone using this proprietary process, we can make a cement that will give you incredible strength. And just to give you an idea of the range of raw materials that we're able to use, so you know that we're not killing mountains and digging holes where they shouldn't be dug. We've done it with lava from Hawaii. We've used a variety of fly ashes from coal plants. We've used rice hulls from the agriculture industry in California. We've used sand from Afghanistan, the Mojave Desert, the seashore, the Jersey Shore, Sandy Hook. Did I miss anything there? And Piscataway mud.
Piscataway mud. That's the stuff from outside our
right.
our building.
And so the compressive strength of a cement is normally around 30 megapascals, and our materials are on the order of about 170 maybe down to 150 megapascals. So you've got a much larger amount of strength that's possible with this. And when civil engineers have the nerve to do it, that means they could actually drop the amount of cement that they would actually use in these types of structures, as well as some of these advanced materials. So I don't see a huge amount of mining going on. And the other reason also is because calcium silicate isn't as abundant as other kinds of silicates like magnesium silicate. The future, as I see it, is magnesium silicate, because it's just about everywhere. We're walking on it when we leave this place, minus the asphalt.
All right, we have a question here.
Okay.
Yeah, my question was regarding IP, but I think you answered it. I'm guessing it's patent protected.
Yes.
The process. And the other question I had was, so how do you plan to sell it? Do you plan to sell like slurries or the material? Is that where you plan to sell, or you want to plan to sell actual products or bricks? So how do you plan to go about, actually marketing or selling your product?
Oh, marketing the product?
Of selling the product. So what's the actual product you're going to be selling?
So we're actually in the business of licensing the technology. So what we want to do is, convince bigger entities that, have the resources to, manufacture large amounts of material, that our way of manufacturing the material is going to save them lots of money. So, again, we, like I just said, the IP it's patent protected, and the core carbonation technology that I was talking about, that's a patent that's assigned to Rutgers University, and Solidia actually holds the exclusive license to the patent in the field of building and infrastructure. And RRTC is sublicensing those rights from Solidia. And we hold the rights to do licensing in about 14 different fields of use. one of them being like the automotive and transportation industry. So that's why we can, use it to work with, the types of materials that would go into that.
Over here?
Two simple questions. On the technology readiness level scale, where you're at with your technology?
I would say that we're probably around a 4. Would you say that? Would you agree, Rick? Three,
Okay.
yeah.
If money was not an object limitation, how long it would take you to commercialize your technology?
Yeah, sure.
One of the big, and I mean big, advantages of this technology is that it's one of the few technologies where you make a material and it's exactly the same size as when you molded it. The only other thing you can think of that comes to mind is injection molding of plastics. Usually with ceramics and even cement and concrete, you have shrinkage, okay? Because you don't have to worry about this with this technology, the lack of shrinkage allows you to make really big objects. So the biggest object we've made to date is 50 feet in length, 5 feet wide, and 8 inches thick. And to even go from something that's this big to something that's this big, when you fire materials, when you heat them at high temperature, it could take you 10 years to actually do. It's very, very laborious because of the mass of the material and the fact that the shrinkage on a linear percentage is like 20%. So when we first commercialized the concrete process, the first product we wanted to make was building facade tiles. Instead of cutting stone out of cliffs, we have some samples we can show you. We make these stones synthetically, and they look just like fired materials or natural granite or marble or any of those things. The commercialization cycle to make a full-size product, including the time to actually get into the building, lease it, get the electricity and the plumbing and all that done, was 4 months. Which is incredibly short.
So basically what you are saying that the fundamental technology is proven, or the fundamental physics are proven, that TRL4 to TRL9 is purely an application timeline for you.
Exactly. It's going to be that. And so what we're actually in the process of doing now from RRTC side, because Solidia is already a company that has about somewhere between 70 and 80 employees, and they're all over the world licensing it where people care about CO2 emissions and want better materials in the road construction and building other infrastructure materials technology. We're right now, what we're doing is we're talking to companies that have problems they need to have solved that our technology solves, as opposed to having a company where you have a solution in need of a problem. So we've got about 7 different conversations we have ongoing right now with companies that have problems, and we are going to work together with them so that the large company basically works with an intermediate company like us, and they get to do what I like to call try before you buy. And then they invest in the full-scale process. We only take it to the pilot plant scale.
Last question here.
Thank you. How did you select the target markets, and could you provide some of the rationale for why those are the best first 2 target markets to tackle?
Well, like Rick was saying, when we discovered that we were able to get 10 times the stiffness of the plastic with our material, the thing that we immediately thought of was like, this is like a fiber reinforced composite. So, and we happen to know that a lot of vehicles and a lot of structural components in vehicles, end up being made out of these reinforced composites. So that was the rationale there. As for the gaskets and seals that I mentioned, we also did a little bit of what's called thermomechanical analysis on our material, and we found that when you have just the plastic, when it reaches its what's called its softening point, it sags like crazy. But with our reinforcement in it, it doesn't sag at all. So that's what made us look at that sort of market.
Kevin, thank you.
All right, thank you.
Great job.
Thank you.
Rick, thank you.